So I'm talking about group of diffeomorphisms, the real analytic diffeomorphisms. And anyway, when I use the blackboard, some of the statements are not so clear. And I should give you the reference. And one is my paper. In Annals Scientifique du ENS, tome 42, 2009, 601, 651. That's it. This is the paper. No figures. And in fact, in order to explain the regimentations I talked yesterday and some other thing, it may help to have some figure. And the figure, you can see the so in, I think, 2015, we have a FET for HNGs, and there geometry math CNLS France but PDF. Here you can see some figures, and I hope it helps a little. And then, yesterday, I said that you can look at, for example, the manifold like S1 cross, if there is a free S1 action, and also, in fact, if it is the product, then you will have, in fact, the projection to the circle. And then there, I say that here you have the obvious vector field generating this circle action. It is just a vertical way or horizontal way. And you can find G1C, GNC, so that they will span the tangent space of this manifold. And then you can form, putting the Riemannian metric on this manifold, you can think about the I1, IN, which is the determinant of the CI1, C. So I should say C itself should be G1C. G1 is the identity, and determinant of GI1 star, GIN star C. And then we will have the positive non-negative real analytic functions like in, for example, square, or to the 4th power or 6th power. And then you can make the partition of unity by the real analytic functions, positive real analytic functions using that. Then you have what I called regimentation. Lemma. And you can decompose any f close to identity into f equal to f1, f and n. So it is something like this. And this diffeomorphism moves only the place where this determinant is non-zero. That means at that place, this locally looks like the not a coordinate, but you have any the n linearly independent vector, and first you go the first direction, and second you will go the second direction, and you can decompose the diffeomorphism of all these things into n that should be f1, 1, f1n, and also all these things are f11, sorry, this number 1, f large n, small n, n. So anyway, I can decompose all the diffeomorphism very close to the identity into the product of the orbit preserving diffeomorphisms. Okay? And their first remark is that, in fact, I didn't use the fact that Cusi is non-singular. You can use the singular vector field. For example, the most, I think, important circle action is the Z, oh no, C to C. So U1, of course, acts on the complex plane in such a way that U of Z equal to UZ, and U is the complex number, and U, the absolute value of U is 1. This is a circle. Yeah, it is the simplest, but it should have the generating vector field you can write down easily, but it has the singularity. But you can use also these things to as a member of this Cusi, and also you can decompose the diffeomorphism into the diffeomorphism which preserves the orbit. And also, in this case, the vector field here should be 0, of course. And then you can make, you decompose these things to the orbit preserving diffeomorphisms. But if you are using this vector field, the decomposed one can be made as flat as possible at the origin. So it is necessary that if you use this vector field, the determinant should be 0 at that point. And if you use the square or the fourth power or sixth power, you can make this diffeomorphism as flat as you want at the origin. Okay? So this is one thing I can do. Very good. So now I want to think about the circle actions. That is U1 times m to m. If you take u and x, usually the image is written like that. And so there are three kinds of orbit. Either free, this means the orbit is so U1 to this one is injective or multiple. So this U1 to the orbit is, it has some of the points go to x itself, and that should be, it is rather, here in the circle you will see z of n. That is the cyclic group of order n in it, and this will go just to x. Then the orbit is n-fold multiplicity n, or the fixed point. Fixed. And we put, it is, I think, you already learned somewhere when you are doing the course of manifolds, and we put U1 invariant metric, and then a neighborhood of these orbits are classified. So in the first case, it is U1 times the n minus 1. So it is just free. And the second thing is U1 times dn minus 1 divided by zn, where zn in dn minus 1 is in the on. And these are always something like Z1 Zm or Z1 Zm and x to so e to the n 2 pi k1 I z1 like these terms. Or it is also the same thing, and the last thing is plus minus x. So this is a multiple orbit. And for the fixed point, the action is, so this is only, the neighborhood is the n itself. And the U1 should be in O, sorry, this is not n. And you should have U1 in ON, and you will see almost similar expression that will give you U Z1 Zn M should be U K1 Z 1 U K M Z M. So this is the even dimensional case. M is the half of n. Or Z1 Zm, some one dimensional thing. And this is just the same term, and x itself is identity. And you will see in dimension 2, there are not so many. So either you have annulus or Möbius band. Yeah, more or less this. Okay? So if you go in the center, it flips once. Or this concentric circle. And in dimension 3, so either 3D torus in the free case, or what you know about the center of the Seifert fiber. Seifert fibration, you have some multiple fiber, and it is almost the same figure, but you will see a kind of torus knot converging to the center. Or, so this one times the interval. Okay? So there are not so many locally, but what I want to, if you look at this list, so I wrote already 15 years ago, I explained that something like 10 years ago or 9 years ago. There are not so many progress from that time, but I want to propose a kind of proposition which should be to be proved, that if I have if there is U1 action, U1 manifold Mn, there is equivalent map to C with there exists K such that there exists equivalent map to the action that U Z equal to U to the kth of Z. So if you think about the category of the all UR maps, then there is a kind of final object or a series of final objects that every UR manifold is equivalently mapped to the plane. I can show it in many cases, and I'm very, very sure that we can prove it. Okay? Then I want to at least explain you the case of the spheres. And the case of the S3. And so in this case, so S2 is usually drawn like that. And here you will have XYZ axis. And you can see this proposition is true because if you look, there are the rotation around, there are rotations around x-axis, y-axis, and z-axis. Yes, please.
In the proposition, is there any assumption on the U1 action on the manifold? Is it analytic? Is it
Analytic.
semi-free? Is it
Semi-free case I can prove. And then analytic, yeah, I think I can prove, but I will not read, it is not written. So this is, I think any differentiable thing should be written in this way. Yeah. And if it is analytic, some interesting thing happens. I mean, I tell you. Okay? Any other questions? So, so there are rotations, of course, and if you look from above in the direction of z, and then you will see x-axis and y-axis, and rotation around x looks like the orbit is just the, how do you say, latitude lines. If you think the North Pole is in the x direction. And this is the orbit of rotation around x. And orbit of rotation around y looks like this. And these two, if you look from the z-axis direction, it looks like that. And so what I want you to do in the regimentation lemma can be done. But if you are on the sphere, it is in fact looks something like that. Oh, not easy. You see. So here, all the around the equator, two circles, the orbit of the rotation around x and orbit of the rotation around y are tangent along these things. And so if you look at these determinant, then here, not on the equator, the determinant is not 0, but around on the equator, it is 0. But you can make the by this decomposition as flat as possible, and if it is flat enough, then every diffeomorphism near to the identity and sufficiently flat along the so you can decompose the diffeomorphism like orbit preserving diffeomorphism. Okay? And so now I have if I have F is a diffeomorphism preserving each concentric circle. And here, of course, we have R alpha, Diophantine rotation. And I want to use this Diophantine rotation to show our result. And in fact, so, well, in this case, for example, if F is near identity, and F at the origin is that of the identity, and I think that should be some condition K flat, maybe 4 flat, somewhere there. Then, so this Diophantine rotation composed with this F is in the very near element, which is close to the rotation, and we will have some collection term, and this becomes the rotation number alpha, and there exists H alpha H inverse. So in this case, there exists lambda and H such that this thing happens. And also H is orbit preserving. So I'll do the argument of the Arnold orbit-wise. And if you don't have this singular point, it is contained in the parametric version of the Arnold theorem. But it is also true if the rotation in the center is already, so it is a fixed point. And if this one is close enough to the Diophantine rotation. Okay? So this thing you need to prove, and it's a kind of the Fourier analysis. So you look at the paper by Ellman, and he wrote about this parametric version. And so you will just write down everything with this, or no, with this, with the rotations with the singular point. And by chance, it is true. So if you can do it, 3. Okay. So if you can do it, what happens? That is, this every along the every orbit, I can do these things. And there is some small what? Tip? So if you write R lambda R alpha F equal to H R alpha H inverse, so we are looking at something, some manifold with the circular action, and on that manifold, rotation along this orbit has the well-defined meaning. Okay? So this part, and this has a well-defined meaning, but in order to write down everything, you have to take some trivializing orbit. So this part may depend on your trivialization. And the first thing, this lambda is unique. That makes the rotation number of R alpha F equal to so this is the rotation number of the R lambda R alpha F should be that of alpha. And this function is strictly monotone increasing with respect to this lambda, and you have a unique solution lambda. And also, in order to take H, you can choose. So other choice of H is in fact H of some R beta can do, because if you change this H by H R beta, then H R beta, R alpha, R beta inverse H, and this is the same. So you can choose either this one or that. So in order to make it unique, you will impose that H minus identity. There is this kind of normalization somewhere. So this on the orbit equal to 0. Okay? So if you impose this thing, then this H is unique. So everywhere things are unique, they are somehow patched together to give the global diffeomorphism. So that's good. And I said what I should say. And another thing, so all what I did, I arrived that if F is close to identity, so F is homologous to, in fact, orbitwise rotation. That means if you look at the same, and then this part comes to here, alpha inverse, and this is a commutator, that means F is homologous to R minus lambda. So everywhere you can do it, and F is homologous to orbitwise rotation. That's good. So I thought I proved almost. And then before, in the first talk, I explained Ehrman's proof. And there also you found some small rotation. And the rotation, you use the action of the PSL2R or direct product of PSL2R to write it as a commutator. So the strategy is we want to write this orbitwise rotation as a commutator or two commutators, a product of commutators, by using orbitwise SL2R action or SL2R You can also use its universal cover if you want. So you need some coordinate reference to make it act SL2R, because the usual action of SL2R is just as you think. So SL2R acts on the plane in such a way that the half line origin of the origin, how do you say? Half line rays from the origin, it acts. So or so I want to make SL2R act on U1, but U1, so it is U equal x plus Iy. And then the most important element here in the SL2R is A inverse. And so if I write this one A U is of course A times X plus I times Y over A, but this one was the norm 1. This is not, so I should divide it X plus I. This is the action, of course, on the place. So in the case of S2, I began talking on S2. You have your coordinate. So for your thing, so in SL2R, you can just calculate in such a way that you can write down R theta can be written as A 0 0 A Y R half of theta and A 0 0 A. And here Y is some element. The difference of the Y from the identity is something about 4A minus 1 theta something. So the rotation can be written as two commutators smoothly, but you have to be careful if A becomes 1. That means if you want to use the identity here, it is not good. Identity commute with everything. But you can see if this theta is divisible by a minus 1, then this expression, everything is real analytic. So in the real analytic category, you can do division. This is very important. On the smooth category, you cannot. So this expression is real analytic. Okay. So what happens, in fact, in my case of the rotation?
Can you say what you mean by divisible?
Divisible means.
That's your angle, right? Do you mean like it's a minus 1 times pi times the rational?
Say again?
Do you mean theta?
These are numbers. These are the, in fact, function feature constant on the orbit. And this is a function, real analytic function on the, for example, 2 plane, and which is constant along the orbit. Yeah, I have a good. So this means I have some kind of the family of rotations which can vary. But as far as until now, in some sense, this rotations are written in a real analytic way. Okay? So the theta there is that real analytic function. And I want to take the hyperbolic element depending on the orbit. But this A also should be the analytic function on the plane, which is constant around the orbit. And if theta is not 0 and A is not 1, then there are no problem. You can do. But when A becomes 1, because at the origin, it is expected that A become 1. And then if A becomes 1 here, and this rotation should be so small that you can divide it by A minus 1. Okay? And in the, so I don't know. I will say some word I don't know well. The sheaf of the real analytic functions are coherent. And in that proof, you have to use this divisibility. And it is also called Weierstrass preparation theorem, I think. You can, if something is 0 along some real analytic set, you can divide by that function. Yeah. So here, somehow I explained that you can control the rotation in such a way that it is sufficiently 0 at the origin, and then using that formula, you can write all these rotations, small rotations, by a commutator. So that's, I think, good as an explanation for S2. All right? And then S3. And this S3 has also the same kind of rotation. You can do using the S3 has the most known U1 action is the hop action. It's a diagonal action. So this is a free action, beautiful free action with the defining the hop vibration. And we learn, I think, every year. But you can, here you can also use the action like, so it can be seen also, there is x, y, z, w real axis, and the rotation around, for example, xy plane is some rotation very near to that one. And you can use that thing to write down the same proof. But you can also use this hop action. And this is a little more interesting because hop vibration is not trivial vibration, of course. And if you want to, for example, make act SL2R, you need to have some trivialization. And since it is not trivial, you have to crash several orbit, one orbit in fact. And this action also satisfied my proposition because from S3 to the C plane, Z1 or Z2. So if you have this U1 action, then this is also the canonical U1 action. So you have this thing. Okay? So the point here is from all these things, I have orbit-wise rotation for this vibration. So if I have F diff omega S3 0 near identity, F is homologous to an orbit-wise rotation. And I want to make SL2R orbit-wise. I want to make some orbit-wise SL2R action on that. So in order to do that, I can use this proposition. And it's a kind of very subtle thing that happens. So here you see the concentric circle, and there I know how to make act SL2R orbit-wise SL2R action. In fact, orbitwise SL2R action here should be written in this way. This is very near to that expression. And A Z equal to something like I should write in this way. It's better. And times C. And here AZ equal, if the same formula as that, that is AX plus I times Y over A. And this expression can be written in my way that AZ or AU over a absolute value of AU. And in order to make A act on the concentric circle, this is not radius 1. So AZ should be make them radius 1. That means A of Z over Z, A of Z over Z, and then radius should be Z. And since if you look at what is happening here, you can erase this absolute value of Z, and then you can write again to make this formula. It is not, it's a kind of calculation, easy. And what is interesting as a calculation, we have to see what happens at the origin. And so I want to say something like this expression is real analytic even at the origin. So I want to make this part not 0. So this thing is after 2 lines of calculation, you will see 1A plus 1 over A plus A minus 1. It is quite elementary calculation. Yeah. I will find some easy formula like this. And then what is wrong or good? So it means if A minus 1 is divisible by ZZ bar, then if it is divided, it will give you a real analytic function. Then all other things are, in fact, Z bar is real analytic. Not holomorphic, but it is real analytic. So this expression is real analytic. So you can use it. And then what does it mean? So if I have this kind of action on this concentric circle, the other thing is I have this projection, and this projection, in fact, how do you say? In fact, describes how the Hopf vibration is not trivial. So if you look at very closely at the origin, you will see something like what I think you write every time. If you want to lift the circle, and if you have some, trivialization, then it will be the trivialization becomes how can I draw it? That should go once around the fiber if you turn. So if you turn once, it will turn once around the fiber. This means the Euler class of this vibration is 1. So what I'm doing is I have this SL2R action rotation, and this rotation really reflects the rotation here. And also, if I have this SL2R action, then it will also act on the fiber. And in fact, in the center, it will converge to the identity, but it is real analytically converged to the identity. So in order to make it everything work, this part, the rotation, rotation and this this one. So I just said if it divides, then it's okay, at least on the plane. But in order to make it okay along the fiber, it should be, for example, if this one is more flat, 3 or 4, I think, then this action, SL2R orbit twice, SL2R action lifts. And also, if the rotation is sufficiently small, it can be written using this action to two commutators. I think I have already used all my time. Thank you very much.